Okay, so welcome back. In this lecture, I'm answering a question that was made by Giovanni after lecture 26. Let me summarize Giovanni's question. In our initial lectures on renormalization group, we introduced the concept of regularization, and the way we do it, we acted on our initial Hamiltonian, which consisted of a kinetic energy term, plus a Coulombic term, if you remember, go back on your notes if you don't, and a short core potential, and we assume this core potential to be a delta function. And then we went from this Hamiltonian to a regularized Hamiltonian, which contained only finite term. So the way we do it, we went from the bare potential to the regularized potential. And the regularized potential was obtained by taking the normal potential, V of R, Fourier transform it to momentum space, add in some kind of regulator, for instance, p squared a squared over 2, and then anti-Fourier transform it back. Right? That was the procedure we adopted. By doing this, we were sure that we would not introduce any divergence in the calculation. Now, the question, in contrast, in field theory, what we seem to be doing is something slightly different. We start from a bare Hamiltonian defined in terms of fields. We leave it bare for some reason, and rather than just regularizing the Hamiltonian, we regularize directly the diagrams, the calculations you make out of the Hamiltonian by introducing in the loops and modifying the loops in order to be restricted into a region of momentum shell. You can do this by introducing a cutoff, as usual. So on the one hand, you were regularizing the Hamiltonian. On the other hand, you were regularizing the diagrams. And the question that your colleague is asking is, can't I just regularize the Hamiltonian as well, even in this case? And the answer is obviously yes, you can. And the way you do it is exactly the same way you would do for this Hamiltonian here. So let me consider the simplest case of a quadratic term. Well, let's do the phi to the fourth. The way you probably do this is to do like phi squared of x, d3 of x, phi squared of y, and then rewrite this as delta minus y. That's a way of writing phi to the fourth, right? Then if you go to momentum space, you can immediately see that you can smear this guy. If you transform this expression to momentum space, perform a Fourier transform of this, and then Fourier transform backwards to position representation, you'll discover basically what this is doing is introducing a smeared representation of a delta here. Now, graphically, this means that this is no longer local interactions. It is a bit like having two vertices and some short distance but finite distance, lambda minus 1, range interaction, which is typically Gaussian. Okay, so this looks like a typical one gluon exchange or one Coulomb exchange, where rather than exchanging a Coulomb interaction here, you exchange a delta type of potential, smear delta potential. But now the reason you normally don't do that is that by doing this, your theory becomes non-local. Interactions are at distance. Physically, it's exactly the same thing as putting a momentum cutoff. But from a mathematical point of view, people tend to renormalize diagrams directly. But in principle, you can renormalize the theory directly, regularize the theory directly. And from the point of view of from the point of view of the final results, there is no difference whatsoever. There is a slightly different issue concerning, one thing we never discussed, and even at the beginning of the course, because it was a little bit too preliminary to make such a discussion, was why don't I regularize the kinetic energy term? Remember, we also have a term, p squared over 2m in the potential. Why don't I just, send it to as well? Well, in principle, you may, but I want to emphasize one thing. The reason we introduced a regulator was that if you don't put a regulator, then your theory will mix low momentum component with high momentum component, soft with hard. Remember why? Because any product would lead to any product of wave functions would lead in momentum space, the momentum times the wave function would become a convolution, remember? And if this guy has large momentum component, then you can pick up a low momentum and bring it into a large momentum, a hard momentum, right? So basically you can, by the interaction, go into the theory, move the theory from the infrared sector where you trust it into the hard ultraviolet sector where you don't trust it. So that's why you want to avoid this by putting a regulator that avoid mixing of very soft modes with very hard modes. So you only mix the modes in the frequency range where you trust your theory. Now, why don't you have to do it with the kinetic energy term? And the reason is the kinetic energy term is actually diagonal in momentum space. And so is actually any quadratic form for fields as well. Which basically means that there is no mixing possible there, right? And therefore, you never have to worry about the kinetic energy mixing low energy to high energy modes, or low momentum to high momentum modes, because it's diagonal momentum mode, and therefore any mode is left invariant by this operator. So this would be redundant. Well, this is an unrequested. This is an answer to unrequested question, but I thought it was worthwhile making it. Okay, bye bye.